Okay, let's walk through Unit 4 homework number 20 through 24. This is the equilibrium problems. These are really tricky. So I'm going to walk you through the process. First of all, I made a nice diagram of my balance beam. I have a 2 kilogram weight hanging down from a balance beam and an 8 kilogram. The 2 kilogram is 0.4 meters from the fulcrum, or that little balancing point. And then we don't know what the other one is, so we'll put in x for that. So now I'm going to solve this problem using a sum of the torques equation. Also, don't forget that the beam itself has mass, so it has 1 kilogram. So, in order to solve, I'm going to need to have a free body diagram. Let's think about all the forces going on. Some of the forces in the y direction has to be 0, and the sum of the torques has to be 0. So, the forces we've got, in the green, we have the 2 kilogram, that's a force down. We have the normal force pushing on the bar up. That's the little balance thing is pushing up on it. And then we have the 8 kilogram down. We also, I haven't shown it because it's just kind of would get messy, is that 1 kilogram of the beam itself. You can put that little free body diagram, make it, in fact I'll put it here in orange. You could put that force right here in the middle. So that's going to be 1 kilogram times 9.8 meters per second squared. In other words, let's put all of the weight of that beam right smack in the middle of the center of mass. And then we'll use that in our calculations. Okay, so I have two equations. So some of the forces in the y direction is 0, and then the sum of the torques is going to be equal to 0. And remember, torque is Fd sine theta. So here we go. First of all, I'm going to find the sum of the forces. So I've got negative 2 kilograms times 9.8 meters per second squared, plus negative 8 kilograms times 9.8, minus 1 kilogram. So that's all of the masses, okay? And then I'm going to have the normal force as well. And so that is going to add up to give you 0 because this thing is in equilibrium, it's not moving. Knowing that, I could solve for the normal force. I only have one unknown in this particular equation, so I can solve and find the normal force is going to be 108 newtons or 110 if you want to round off for sig figs. Okay, let's now find some of the torques because that is going to give us what that value of x is. We need to figure out what it is. Now, if you just eyeball it, you could probably try to figure out based on proportions. So take a good guess, and then let's run through the equations systematically so that you'll know how to do this type of problem. Okay, so the sum of the torques around some point is 0. Now, I typically will choose the point for my torques that is where you have a rotation or where you have a hinge. In this case, it's going to be right where that fulcrum is, right there in the center. So I'm going to find the force on the torque on each of the masses at that center point. So I say torque around the center is equal to 0. So here we go. The first one I got 2 kilograms times 9.8, that's the force. And then I'm going to have times 0.4 meters. Okay, that 0.4 meters is the lever arm. Okay, now technically I should have times a sine of theta. So the sine, well, the angle between the force and the lever arm is actually 90 degrees, so that's going to become 1. So I don't really have to worry about sines of thetas for this particular problem. So I just have the F times the D. Remember, the first part is the F, okay? F times D. So I got the first one, okay? So that is going to cause it to rotate in which direction? Let's ask ourselves. So it's going to tend to rotate it. If we just had that one force, that's going to make it rotate counterclockwise, which is positive. That's a positive torque. So we're going to leave that as a plus sign. Okay, now let's go to the other one. 8 kilograms times 9.8 meters per second squared. Now the lever arm is x. Okay, so that lever arm is x, and that force is going to tend to rotate it in a clockwise direction, which is negative, which is why you have the negative right there. Okay, and then finally, the only other forces acting, we have 108 Newton force right at the center, right? That's the normal force that we just found up here. But because it's acting at the center and we're finding the rotation around the center, there's no lever arm. So I'd say it's 108 newtons times 0. And I left off here, but I should have included, it's also 1 kilogram times 9.8 times 0. In other words, the mass of the beam itself isn't causing any net torque because the lever arm is actually 0 if you're talking about the torque right around that fulcrum. So add these all up, you get equal to 0. So now let's go ahead and solve. What do we have in here? X is the variable we're looking for. So we're going to solve for X. I'm going to realize that first part of the problem is going to cancel out. So I go 784 Newton meters, that's the first chunk, minus 78.4 times X equals 0. Solve for X, and I get 0.1 meter. And if you look back at the problem, that makes sense, doesn't it? Because 2 times 0.4 is going to give you 0.8. So what times 8 is going to give you 0.8? Well, 0.1. So when you do simple balance beams, you can actually just kind of eyeball it and realize it's going to be the mass times the lever arm is equal to the mass times the lever arm, as long as it's a nice, even, symmetric balance beam like this. Okay, but next problem. Okay, I've set up the next problem, and what I've drawn is two different sketches. The first sketch is the diagram of what's happening, right? We have the rope pulling, it's a 50-degree angle. The beam itself is a total of 1.6 meters wide, and it's 4 kilograms. So that's all the information. And then I draw a separate diagram on the right, which is the Freebody Diagram, which is just identifying the forces. So here's all the forces I got. I got the tension of the string at a 50-degree angle. We got that. And then the beam itself has weight. It has 4 kilograms of mass. So that's going to be mg down. And we're going to put that, again, right in the center because it's a nice symmetric beam. So that lever arm is going to be 0.8 meters away based on the symmetry of my diagram. And then I had these two forces. I put an FHX and an FHY. So those are forces at the hinge. We don't really know what's going on over at the hinge. There's going to be forces there because the rope is pulling to the left and there's something going down. So there's definitely going to be X and Y forces. But we can actually eliminate those variables when we do our torque equation. I'll show you how in just a second. So let's start by doing a sum of the torques. So I'm not even going to deal with the forces. We're just going to go straight to the torque equation here. So let's figure out what they are. The first one is the tension. Okay, I got the tension force, and then I got the force times the lever arm, in this case is 1.6 meters, and then times the sine of 50, because this one is not a 90-degree angle, so sine of 50. And then I think about the direction it goes, and that's going to cause it to rotate in a counterclockwise direction, which makes it a positive torque. So that's why I put the plus sign. Okay, so that is going to cause a torque. Now let's talk about the mg, right? The mg is acting in the middle. So I've got my mg, and the lever arm for the mg force. Again, in every case, I'm talking about what's going on here at this hinge, right? That is where this rotation is happening. So the lever arm for the mg force is going to get torqued or rotated around is mg, that's the force, times 0.8. That's the lever arm. And then sine theta is 90 degrees again, so it's just 1. Now we have to ask what direction. Is it going to be positive or negative? Well, that mg force is going to tend to want it to kind of rotate around this way, which is clockwise, which is negative. So we put a minus sign out in front. Okay? There. Now I've got, if you check it out, I know m, I know g. The only thing I need to find is ft, so I'm trying to solve for that. So there I go. 1.23 ft equals mg times that lever arm. And I solve for ft and I get 25.6 newtons, or 26 newtons if you want to go with 2 sig figs. Next problem. Okay, 4.22. So in this case you have a diving board, and the diving board is clamped on one end, but then it has a little kind of balance point 1 meter away. And imagine someone's going to walk out to the end of the diving board, right? So the question is, what is the question? Find the downward force the clamp exerts on the board. Find the upward force that the support exerts. The board is in equilibrium. So we want to find the force that is pushing up over here. Okay, the force is pushing up over here. And then what is the downward force over here at the hinge? That's the two things we need to find. So here we go. We're going to find all the forces in the y direction. So what we have the force of the hinge in the y direction. Again, we don't know if it's up or down. We're just going to write it as up and then figure out what happens in the end. Hopefully we'll get some answers once we figure it all out. So we got the hinge force going up, the normal force going up, and the mg force going down. That's the mg of the board itself. So if I keep going, I realize that I can't solve yet for the hinge force because there's two unknowns, both the normal force and the hinge. I don't know either one. So now I'm going to resort to my torque equation to try to find one of those two. So I'm going to find the torque around the hinge, because then there will be no lever arm for those hinge forces, and I won't have to consider them in my calculation. So let's find the torque around that hinge, and I'm talking about this spot right here. Okay, find that torque right around there. I can't seem to get my pen to work. There we go. Find the torque around there. So I start with the normal force. Okay, the normal force times the lever arm. The lever arm is going to be 1 meter, and times sine theta. Theta again is 90, so sine theta is 1. And then is it positive or negative? Okay, that's going to tend to rotate it counterclockwise, which is positive. Okay, what about the next force? That's going to be the mg force. The mg force is acting down. So the force is mg, 150 kilogram times 9.8 meters per second squared, and the lever arm in this case is 1.5 meters. And that one is negative because it tends to rotate the thing around in the clockwise direction. Okay? So notice my complete equation. Now I have one unknown in this equation, so now I can solve. Now notice that I didn't have to include the hinge equations, the two forces for the hinges, because there's no lever arm. The lever arm times 0, those terms go away. So I solve for the normal force, and I get about 2,200 newtons. Now let's go back and find the force on the hinge. Okay, so now we can take this value that we just got and we can plug it into that sum of the forces in the y direction equation. And we're going to get that the hinge force plus 2,200 newtons minus mg is equal to 0. And so I find that the hinge force is negative 730, which means if it's negative, it's got to be pointing down. So I assumed it was up, but in fact, since I got a negative answer, I know it's actually down. Okay, 23 and 24 about moments of inertia. You have a beam or a rod and you want to rotate it around its end or rotating it around its center. So the question is, what is a moment of inertia for each? If you look on your formula sheet or you look in a textbook or you look online, to get the moment of inertia of a rod that's symmetric rotating around its end or around its center, it looks like this. So I is 1/3 ml squared for the one going around its end, and 1/12 ml squared. Hopefully you see that the 1/12 is much, much smaller. It's much easier to rotate around the center than it is the end, because the more the mass is located closer to where it's rotating. So now I just got to plug and chug. Plug in my m, plug in my l, and solve, and I do. Okay, so 1/3, 0.3, 1.2 squared. Okay, so that are my two values. Notice that the moment of inertia for the rod around its center is much, much smaller. Okay, and then finally, number 24. Number 20 says, force is by what factor does the moment of inertia of a sphere increase if the diameter is doubled while the mass is kept constant? So, moment of inertia of a sphere is 2/5 mr squared. If you double the radius, oops, that's weird, something weird's going on. If you double the radius, then and you square it, you're going to have 4 times the moment of inertia. So you get a sense that having a larger sphere has much, much larger, because that, remember that radial distance, that's kind of the key factor here. So if you have a larger radius, then you're going to have a larger moment of inertia. And that concludes